Okay, um, here we go. So, okay, the book chooses to present it this way, and that's fine. We'll go with it. But this is a very, very, very important day. This is the day which we see the formal definition of the instantaneous slope / rate of change. And so, if you notice, before we've been talking about, the real problem that we deal with calculus is that we want to find the slope of a function at one point. We want to find the slope of that tangent line. The problem is that how many points do you need in order to find slope? 2. And we only were given 1. So what did we do at that second point? We brought it closer. So the limit, we use that idea of limits, that Q approached P, and that, that distance between them became very, 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 very small. So we said, all right, if we want to truly solve that type of a problem about instantaneous slope or rate of change, then what we need to do is we need to learn more about limits. So we did that, right? In fact, your first test asked you to identify limits. You guys learned the precise definition of a limit. And now we even learned about continuity to talk about functions at all sorts of given points along open intervals. So now we are ready to put it all together and be able to say we can have a formal definition of instantaneous slope or rate of change. So what I love about this is that this changed the world, what you see today. This is not technically the formal definition of the derivative yet, but this is amazing. And second thing is that what I really love is that you guys will understand this 100% completely. So let us draw our shapes. We will name it. What should we call it? Function f. You're particularly worried about this one spot right here. We're going to pick a point A. We're going to pick a point A. That's an A. If that is A, okay, if that is A, tell me what the Y value is. F of A, very good. Now, what we want to do is we want to be able to write an expression that gives the slope of that tangent line. So that would be the instantaneous rate of change. Slope is always synonymous with average rate of change. Average velocity, all those pieces come together. But in this piece right here, we are looking for the instantaneous rate of change, or the slope of that green line. How many points do we need? We need a second point. I will draw my second point, only this one is going to be different. This is beautiful. We're going to call this point A plus H. What is my output? F of A plus H. One last step before we can finally do it. What is the difference? What is the distance between these two x coordinates? H. As this is A, This is a plus h, so the difference between the 2 points is h. Yep, exactly that. So here we have it. Slope is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. A for the day, what is y sub 2? F of a plus h, what is y sub 1? Minus f of a divided by, what's x sub 2? A plus h minus a. What happens to the a's? They cancel. Now, no, hold on. You guys, you're almost there, okay? If I want, what I've done right now is I've written an expression that shows me exactly what the slope is of that blue line or the secant line. If I want to find the instantaneous rate of change, focus on this. What should I move h towards? Stop. 0. H is the difference between, I move a plus h towards a, but h is the difference. So h gets smaller and smaller and approaches the number 0. So in order to move it smaller and smaller, I use a limit. Ben is 100% incorrect. He might fail the course due to his lack of substance in theory. We put the limit in front of it. The limit as h approaches 0 of f of a plus h minus f of a all over h. This is how we find instantaneous rate of change. We can now do it. There's no more approximating. This is 100% exact. It is sound in mathematics. Why? We have proved limits by the precise definition of a limit. We have talked about continuity, and we know that this works. So let's now choose our new problem, which says find an equation of a line tangent to a given function at the given point using this first definition. And I'll show you so easily how it works. We have this graph. F of x is equal to x squared minus 3. I'm going to quick make just a little sketch here. What does x squared minus 3 look like? It's a parabola. Very good. 1, 2, 3. Now you tell me, at the point 1, negative 2, I want the equation for the line tangent at that one spot right there. You estimate. You tell me right now would be a reasonable guess. Make a reasonable guess at the slope. Positive 2. Give me another reasonable guess. Positive 1. Positive 3. We know it's positive. All right. We want to find the slope of that line. We also want to find the equation for that line. So here's the two pieces I set up. I apologize if you don't have enough room for this, but we need two things in order to find our equation for our line. Number one, we need a point on the line. Do you know that? 1, negative 2. Second of all, you need slope. In order to find our slope, you might write down y sub 2 minus y sub 1. We don't write that. In order to find slope, we do the limit as h approaches 0 of f of a plus h minus f of a all over h. That's what I'm going to do. So I have my point on my line. I need to find my slope. What is the function? What's the function I'm using? X squared minus 3. So what that tells us is we plug in a plus h for x squared. A is the number, the number that I'm approaching in for my x values. What number am I approaching right here? Positive 1. So my a value is equal to 1. All right? So let's plug it in. I have the limit as h approaches 0 of, I have to plug 1 plus h into my function. What will that look like? 1 plus h quantity squared minus 3 Do you see the definition? F of a plus h. I take a as 1, you said, so 1 plus h, and I plug that into my function. So 1 plus h quantity squared minus 3. So we just did this piece. Minus f of a. What do I get if I plug 1 into the function? -2. So minus the -2 or plus 2. Divided by what? H. Very good. I can now see where this is going to go. Let's apply our theory of limits. The limit as h approaches 0. We practice solving things like these in section 2.3. So let's do it here. How do I do 1 plus h quantity squared? H squared plus 2h plus 1. And then I have a minus 3 and a plus 2 or a minus 1 all over h. What happens? The -1 and the +1 go away. What happens with the h's? This one of those goes away, and this one goes away with that one as well. So I'm left with an expression that says the limit as h approaches 0 of h plus 2. Am I now allowed to plug in my limit? I'm now allowed to plug in 0 for h. That's equal to 0 plus 2, which is 2. So I've just answered the question, what is the instantaneous rate of change? What is the slope at that one spot? It is exactly 2. So the slope is this, which is, we said, 2. Can I now write my equation for my line? I can. Let's finish that off. I have +1, -2 is the point on the line, and I have m is equal to 2. So y equals 2x plus b. What do I plug in for y? -2 equals 2 times 1 plus b. -2 is equal to 2 plus b, or -4 is equal to b. So my final equation for my line, y equals 2x minus 4. And sure enough, we could graph that along with our original function. It would be exact. Yes. Now, we don't have much time left here. We get out in, what, just a few seconds? We need to come back to that tomorrow. But you know how we designed that, the a plus h and the a, and we subtracted them? That's something you're going to need to remember. So we'll come back to that tomorrow. This is the beginning of differential calculus right here. You are ready to take derivatives very soon. So, yes, it is exciting.